everyone, and welcome. I'm Whitney Espick, CEO of the MIT Alumni Association, and today the association is delighted to bring you the latest installment of our MIT Alumni Forum series, Quantum, the Hope, the Hype, and the Glory. Over the next hour, you will be treated to an orienting primer on this topic, which sits at the intersection of many disciplines here at MIT. Whether you are Course 6, Course 5, or Course 8, whether you are knowledgeable about the field or looking to make a quantum leap, if I dare say that, I promise that you will leave this session thinking bigger about nature's smallest phenomena. To guide you in your learning journey is dark matter and particle physics expert Peter Fisher, the Thomas A. Frank Professor of Physics at MIT. The author of What is Dark Matter, Professor Fisher formerly served as department head in physics and is now vice provost for research and serves as head of the new MIT Office of Research, Computing, and Data. Joining him is Ford Professor of Engineering Paola Capellaro, who I would call an MIT triple threat, in that she is a professor of physics and a professor of nuclear science and engineering, as well as an alumna who earned her PhD in Course 22. You will be hearing a bit from Professor Capellaro later on as she offers her insights as a leader in the field. Then she and Professor Fisher will answer your questions, so get them ready. And so, Peter, I think over to you.
Thank you, Whitney. It's always good to hear from you. And welcome to everyone. I'd like to thank Whitney for putting this together, and Ellen Stahl and her team for making this event happen. And welcome Paola Capellaro. So the slides for this talk should be available on a link, and I've actually annotated the slides quite a bit because this is complicated stuff. It might go by fast and you might want to go back and look at it. And so you can use the annotations as well as the slides, and you might want to open them now. Also, while I have this in mind, there's a little critique or review. I've been giving this talk quite a bit and I'm trying to improve it, and your comments really help. So with that, let's get started, and I'm going to go ahead and share screen. So I want to tell you about quantum mechanics as applied to quantum information. And I chose the title, The Hope, the Hype, and the Glory, because we're right at just kind of a wonderful moment where there is this tremendous potential that we can see in quantum mechanics to bring forward a new era of computational ability. Of course, with anything of great promise, there's a lot of hype, a lot of people running around making claims and actually spending money in the hopes of great success. And then there's the glory, and I think Paola is really going to talk about the glory. Because she's going to talk about what's actually happening on the ground at MIT. So in the next 30 minutes, I'm going to just go through a few slides, starting with 2 slides about the limitations of classical computing, and they're really physics-based. And then I'm going to introduce you to the fundamental unit of quantum computation and storage, which is the quantum bit or qubit. And we'll do this building on the idea of a bit, which you're probably familiar with, and understand kind of the key thing to a lot of quantum mechanics, which is the principle of superposition, which is really a particle being in 2 different places at the same time. And I'll show you why that's really okay. It's not that bad. It comes from the wave nature of particles. We'll explore that a little bit. And then we'll talk about how a quantum computer actually processes information through entanglement. And I'll conclude with the big punchline of the talk, which is how a relatively small number of quantum bits or qubits can hopefully carry out enormous calculations only possible in the largest data centers that we have now. Throughout the talk, I'm going to refer to classical computing, which is the computing that we do now. And if you're watching me, you're using a classical computer. It's the laptops, the desktops, and the big computing clusters in our data centers. And they've have their own remarkable story, which you'll hear about in other venues. I'm going to conclude with a little discussion about quantum sensing, which is very important, and we'll set things up for part of Paula's talk, and then quantum error correction, which is the big topic in the field that I don't think gets talked enough about in public venues. So let's start, and we're going to talk about computing large and small. So here's the small. What you see and being held by the two blue gloved hands is a 12-inch silicon wafer with about 144 integrated circuits, which are the active elements of computing patterned on them. And these large wafers are processed and then cut up, and the individual pieces of silicon with the computer on the packaged in a way that is robust and that you can use. This is a tremendous story of technology over the last really 100 years. And I've mentioned Moore's law is not forever. So Moore's law is been around for over 50 years and was coined originally by Gordon Moore, the founder of Intel. And it's simply the observation that the density of circuits on we are able to put on a silicon wafer doubles about every 18 months. So that means the complexity of a computer that we can build at a given power level and a given size doubles in less than 2 years. And that's been happening for the last 50 years. And it's an incredibly remarkable story. However, this can't go on forever, because the little wires that are embedded in the silicon connecting the processing elements are now about 2 billionths of a meter across. That's a nanometer, 2 billionths of a meter. And 2 billionths of a meter is 4 atoms. Now, the problem is, if you make those wires much smaller, it'll get down to 2 atoms and eventually 1 atom. And it's hard to make anything smaller than an atom, because an atom is really kind of the smallest thing there is, at least in the context of this discussion. So that's not going to happen tomorrow. That's not going to happen next year. But there's a decade or two that we have to figure out what to do to keep this kind of exponential increase in our computing capability going. Now, there are all kinds of smart people at MIT and other places, but mostly MIT, working on this. And one of the things they're going to do is exploit the third dimension. So computers are now 2-dimensional, and there's a technology called FinFET, where circuits are actually going to be put on fins that stick up out of the silicon. So for the next decade or so, we're going to be okay. We're not going to run out of computing capability, but we do feel the need to get started, because our demand for computing is not going to go away. In fact, it's increased enormously in the past year with large language models and artificial intelligence. Okay, that's the small. Here's the large. This is the largest data center in the world. There are about 100,000 computers inside this building. It's in Inner Mongolia, near a huge hydroelectric dam, because it needs about 100 megawatts of power. And this data center is able to store and process 1 billion bytes. That's called the exascale. So billion, or 1 with 18 zeros. And there are about 100 data centers of this size in the world. And there are some smaller data centers. MIT has its own data center in Holyoke. But this is really as big as it gets. And we put all of these computers together because one of the great advances in the past 2 decades has been cluster computing, where by co-locating huge numbers of computers, up to 100,000, very complex calculations can be carried out by the computers working in concert. And for that to happen, they need to be close to each other. The thing of this is, if there are about 100 data centers of this size in the world, if there were 8,000 data centers of this size, they would consume about 30% of the world's electrical output, world's energy output, not just electrical output, but total energy output. So that's a bound. And so we're bounded by how dense our computers can be, how small we can make them. We're also bounded by the number of data centers that we can make. And it's something like a little more than the exascale. Again, we will not hit this limit for a couple of decades, but if we want to accommodate the exponential growth in computing that we feel we need, we better start doing something. Fortunately, in 1981 at Endicott House, there was a conference where a number of these ideas came to the fore, and I really date that as the start of thinking about quantum computing. And there were a lot of the principals there, Peter Shor, Richard Feynman, and others. And ever since then, MIT has steadily been building up more and more activity in this area. Okay, so we need more computing capability. And how do we get it? I'm going to start by talking about how we store information in a classical computer, and then tell you about how we store information in a quantum computer. You're probably familiar with the bit. There's the claim it's a backronym for binary digit. Maybe that's true, maybe it's not. But it is the simplest and smallest piece of information storage. And I've shown you a physical realization of that in the upper left by showing you an egg carton, 2 images, one storing a 0, the other storing a 1, just by depending on which well you put the egg in. And the whole point of storage is I can put my egg in one well and I can go away for a day or a week, a month, a year, and I can come back and the egg will be in one place or the other. And that's storing information. When we talk about computing and computer science, we really want to abstract the notion of storing information from a physical realization like an egg carton or an electronic circuit to a model system that captures the idea of storage. And that's shown below the egg carton in the two wells with the red marker showing whether the bit is storing a 1 or a 0. So when we talk about programming, when we talk about information, we talk about abstractions, and then the engineer who actually has to build something takes the abstraction and makes a physical realization, either using a relay shown in the upper left, or vacuum tubes in the lower left. Most bits these days, of course, are stored in integrated circuits. There was this bizarre idea of using airflow in these specialty channels as a way of storing a bit. Yeah, that would have worked. Probably wouldn't have been the best way to do it. But the notion of a bit is really just a way of storing a 0 or 1. And we just think of it like the egg carton or the abstraction that I've shown. Now, I want to move to the quantum bit. And quantum always means going to very small dimensions, atomic size, again, a billionth of a meter. And so what I want to do is zoom in on one of the wells and show you what a particle looks like trapped in the well. And you've probably heard that quantum mechanics describes particles using waves, and I'm going to illustrate that. And the point I want to make is that the size of the wave is inversely proportional to the mass of the particle. So the heavier the particle, the smaller, the narrower the wave is. And that's why you don't see, the coffee cup on your table jumping around. Is in the quantum world, it's very, very heavy. So it looks like it just sits there. But if you had a coffee cup with the mass of an electron, it would be sloshing all over the place because it's actually a little wave. And on this slide, I have a little graphic that illustrates this. I'll warn you, the graphic glitches quite a bit as it starts. And that's a fun feature of PowerPoint. But what the graphic shows is there's the orange curve, and that's just the bottom of the well. And you can see there it's marked out in distance of nanometers. So the numerals are about 2 nanometers apart. And then the blue bump is the wave of an electron with the mass of an electron confined in that well. And what you'll see is that as I change the mass of the electron, the wave, as I make the mass smaller, the wave gets wider and wider, and the sloshing happens faster and faster. So here goes. Okay, so it's glitching a little bit. Okay, now you can see 3 electron mass, 1 electron mass, 0.1 electron mass. And it'll go backwards, and you can see how the place where the electron is, that's described by the blue curve, gets narrower and narrower, the heavier and heavier, and the sloshing gets bigger and bigger. This is just to explain to you why we have to think of a nanometer or a billionth of a meter when we talk about quantum things. Okay, so over on the left is our abstraction. Again, there's 2 wells, 2 places where you can put things. But then what's shown in the well is there's something that looks like a wave or an inverted wave in each well. So the particle, the electron, can be split between the 2 wells. You don't have to put the marker all in one place or all in the other. And this is quantum mechanics. And if you just think about it, if you go back to the egg carton that I showed you earlier and think about some water, say I gave you a 1/4 cup of water, you could divide that water has a wave nature, between the 2 parts of the egg carton, no problem. And this shows you one element of why quantum mechanics, quantum mechanical calculation can be very important, because the qubit, this quantum bit with the wave of the electron split between the 2 wells, can store much more information. It's not just storing a 1 or a 0, because you can store information in how much of the wave is in each well, which is a real number. And you can put a lot more information into a real number than just a single bit or even an integer. So we'll come back to that in a moment. That's the abstraction off to the left. There's some physical realizations on the right. The first quantum computing was done using nuclear magnetic resonance, which uses the interaction of a nucleus with a magnetic field. And actually, one of the very first quantum computers were built by 2 groups at MIT, and using this technique. They had 3 or 4 qubits. And in fact, if you visit the physics junior lab, even now, there's an NMR quantum computer there that our students actually learn how to program. Of course, the best way, or the way many people are pursuing of storing quantum information, are electronically. And the other 3 realizations are shown. There's the transmon, which uses superconducting circuits to store information on the upper left. There's the fluxonium, which actually is invented by Will Oliver at MIT, and that uses a different kind of superconductivity. And then a technique that Professor Capellaro is expert in, of again using the nucleus interaction with light or a magnetic field, is another physical realization of the simple picture shown over on the left. Okay, so that's one way a qubit stores information. Here's a second way. If you notice, the two little waves which oscillate up and down can do so in different ways. Is they can oscillate together, or they can oscillate in an opposite way, or they can oscillate somewhere in between. And this graphic, which does not glitch, illustrates that. So there you see them oscillating together. Now they're a little bit out of phase. Now they're oscillating opposite, a little bit out of phase, and it'll go back together again. And this is a second place that you can store information by the relative phase between the oscillations. So you could say, okay, well, this is going to be a 1, and this is going to be a 0, and then in between is going to be 0.5, and so on. It's determined just by how well you can measure those relative phases. The key point here, though, is that the qubit stores really two real numbers. And that is a lot of information in a device that corresponds to the bit of classical computing. Now, what those little waves are telling you is the likelihood of you finding the electron in one or the other well. The bigger the wave, the more likely it is that the electron can be found. The electron actually is in one of those places. And this is another feature of quantum mechanics, is you don't know where something is until you actually measure. So here's a little way of how you measure or how you read out a quantum computer. And that's using, in this simple example, light. So if you wanted to see if the particle was in the 0 side, which is illustrated on the left, you send in a light pulse. And if the electron is there, the light pulse is deflected, as shown in the lower graphic. And you, by measuring the outcoming light pulse, you'd see that it was deflected, and you would conclude that the electron is in the left side. This is what you would do at the end of a quantum mechanical calculation to see what the result was. Similarly, a lower amplitude light will query the one side and be deflected. And so this is quantum mechanical measurement. The key thing to notice is before the measurement, looking at the left side, upper left, the electron is split between the 0 side and the 1 side, more probable in the 0 side. After the measurement, the system is left with the electron in the 0 side. So the measurement actually changes the information, or actually eliminates the information stored in the qubit, and that information in some sense is transferred to the light. So this is an additional complication for how things can be calculated quantum mechanically. All right, so that's the qubit. That's how it stores information, and that's how you measure it. You can set up your qubit using similar techniques, either using light or electromagnetic fields, depending on the physical realization. But I think you see the idea that the particle is split between these two places, and that gives tremendous power in storing information, storing two real numbers. Okay, but computing is all about processing, and so far we're just talking about storage. How does computing work? When two qubits are close to each other, the pieces of the wave interact with the pieces of the wave in the other qubit. And it's those interactions that bring about a phenomenon called entanglement. And I'm going to dwell on this a little bit, because this is how actually processing happens. So here are two qubits, and I'm just putting this brown oval around them to indicate that they're in physically close proximity, and the pieces of wave are going to interact with each other, because after all, they're just encoding the probability of where an electron is. And as you might remember from 802, electrons push on each other. opposite like signs repel. So the electrons can push and pull on each other and alters each other's state. And through controlled interactions is how quantum processing happens. And so we can just enumerate what those interactions are. So there's the left well interacting with the left well, right with left, right with right, and left with left. So there are 4 interactions that can be controlled either electronically or using a magnetic field. The detail is part of the physical realization. But this is how the 2 qubits will act as a gate to process information. And in fact, these 2 qubits have now formed one system that you can think of as a system with 4 wells that's encoding 4 real numbers. And this gives you the idea that for a quantum computer, every time you add a qubit, you double the number of real quantities that are being stored in that system. This is in contrast to a bit. If you have a computer with a number of bits, adding 1 bit doubles the size of the single integer that you can store. In contrast, a quantum computer, adding a qubit doubles the number of real quantities that you can store. And I think if you think about that, you can see there's a huge difference between the way you can build up information storage in a quantum computer. Okay, so now we have some idea of how processing can work, and we can think about a more interesting thing, which is a gate. And this gate is really just a description of the 2 qubits interacting with each other over a period of time to go from one configuration to another configuration. And the processing or the computation that we want the gate to do is encoded by how strong we make those 4 interactions I showed you on the last slide. So on the left side, you have qubit 1 and qubit 2 going in. Some interactions take place, and you can see that qubit 1 and qubit 2 are altered coming out. So that is the next level of processing, or the fundamental level of processing, 2 qubits interacting. This is an interesting contrast to classical computing. Those of you who have used computers know that there's a central processing unit, and the way computation takes place is the central processing unit extracts data from memory, puts it in registers in the central processing unit, something happens, there's a result that is put back into memory. In a quantum computer, all of the computation takes place between qubits, and no electrons move between qubits. They just alter what's happening in neighboring qubits. And that's shown in the lower panel, where you see qubit 0, 1, 2, and 3 starting out with zeros. And then as you move along, you can see that neighboring qubits interact with each other through gates. Sometimes a single gate just works on 1 qubit, but every qubit, because of the connected nature of the gates, eventually influences every other qubit. And this is a big challenge for coming up with quantum programs, is that you have to program this in a completely different way than you think about programming a classical computer. This is one possible arrangement of qubits, and there are many others that are being thought of. This is still a very young field, and this is called a topology of a quantum computer, and there's no standard topology yet the way there is in the classical computers that we use. Okay, so let's just review. We have bits. The abstraction of a bit is just this 2 places where you can put one object, so you're storing information. Qubit, you have 2 places where you can split an object. You can have the electron in phase, out of phase, so you're storing two real numbers. You put 2 qubits together, with controlled interactions, you can get one qubit to interact with the other qubit and produce a result that you have to encode, and that's a gate. And then you can stack together many gates to carry on a quantum mechanical calculation. And then at the end, to find the result of your calculation, you have to measure in the way I've described it so far. So this slide is kind of a big part of the punchline. This is thinking about, okay, every time I add a qubit, I double the number of quantities, real quantities that I can store. So 1 qubit stores 2 real quantities, 2 qubits stores 4, 3 qubits store 8. So 2 to the number of qubits, if you think that way. If you have 10 qubits, you can store over 1,000 real numbers, 20 qubits over 1 million real numbers, 40 qubits over 1 trillion real numbers. If you have 60 qubits, you can store over 1 billion real numbers. And that's the exascale. And I showed you a picture of this huge data center with its own dam and lake and hydroelectric power and all this stuff. That is storing the same amount of information as theoretically you could store in 60 qubits. This is the hope. And this is also where a lot of hype comes in, because it's really easy for me to say this, but it's really, really, really hard to do. And Professor Capellaro will attest to that. Okay. What's the big problem? Why is this so hard? Remember, this is happening at the nanometer scale, 1 billionth of a meter. Classical computing happens at 1 billionth of a meter, and that works out well because I can just use lots and lots of electrons, and I can just put them where I need them to be put in one side or the other. I don't have to worry about this very careful division to encode information. So the message here is this qubits are very, very delicate, and they're very susceptible to outside interference. And you can think of that outside interference as an unwanted measurement. So some light comes in, it interacts with one or the other sides of the double well, and then it alters the system, thus destroying my calculation. So the hope and the glory coming up is really in quantum error correction. And let me tell you about that. And I'm going to start with classical error correction. So even classical computers can flip bits. And in the early days, this was caused by the packaging that emitting alpha radiation that interfered with the electronic circuits. People worry about cosmic rays, and computers carry out an enormous number of calculations, but you get a few errors and the whole thing will crash unless you have some means of ensuring that the information is preserved. And you do this through redundancy, which I've illustrated here on the left. So if I want to store a 1, I don't just use 1 bit. I use 3 bits, and I put a 1 in each bit. That way, when I go to process that bit, before I process it, I'm going to look at each bit. And if one of them is different, I'm going to switch that one back to what the other 2 are. It's called majority voting. And I've illustrated that with here. You can see the 1 being stored as 3 1s, and then there's a little orangey lightning bolt that's flipping the 3rd bit to 0. I'm going to use the other 2 to vote and restore the information to the 3rd bit. That means you use 3 times the number of bits, but you get a much lower error rate. There are much more sophisticated methods that are used now, but I would estimate that a fair fraction of the electronics inside of a modern CPU are devoted to error correction. Quantum error correction, which has not been yet demonstrated, or at least not sufficiently for practical use, relies on entangling the qubit holding the information that you want with 2 qubits in the 0 state, for example, called ancilla. So the entanglement process spreads out the information from the qubit over all 3 qubits, and then you can measure one of the ancilla qubits while preserving the information in the qubit to see if that's what it should be. And if it isn't, you can reverse the calculation or repeat the calculation. Again, you can view this as a quantum mechanical system with 8 little wells storing three electrons. Many people are working on this, many at MIT. And the thinking these days really is that to store 1 qubit of information is going to, in the abstraction, is going to require hundreds, perhaps thousands of physical qubits. Although I have to say, no one has actually demonstrated quantum error correction of this type yet. Okay. I just want to conclude with quantum sensing because this is something very important at MIT. This works through entanglement. And I told you entanglement is very fragile. And it's fragile under outside interference. For example, the motion of 1 qubit with respect to the other. So you can make a quantum sensor by mounting 1 qubit rigidly somewhere and putting the other qubit, for example, on the cantilever of a probe that's of atomic dimension, so that you can measure the deflection of the probe by seeing how the energy levels of the qubits change. Because when you move 1 qubit to the other, all of those 4 interactions I told you about between the qubits alter. And this is the basis for measuring small electric fields, small magnetic fields, gravitational fields, and time. Okay, so that's what I have to say. I hope you were able to follow it. And I hope you can download the slides and read the annotation, which might bring clarity. Next, I want to introduce Professor Paola Capolaro, who's my colleague in physics and other people's colleagues in nuclear science and engineering. She's the leader of a new effort called Quantum at MIT, and this organization will start soon, and you'll be hearing about it. She's going to tell you about the exciting things going on at MIT, both at campus and Lincoln Labs. And as you know, Professor Capolaro holds appointments in nuclear science and engineering and physics at MIT, and she just became a fellow of the American Physical Society. So with that, over to you, Paola.
Thank you, Peter. And I'm really grateful to be here to be able to present some of the work that we are doing at MIT in this very fascinating area. So I'm gonna go ahead and share my slides. The first thing that indeed I want to talk to you today is this exciting new initiative that we are putting together that we have called Quantum at MIT, which is really promising to, if you want to multiply the effect and the impact that we can have in the broader area of quantum science and engineering. As Peter already mentioned, this area is really exciting, and MIT has played a very important role in developing the overall program. He already sort of mentioned the Endicott conference, but really so many other forces that happen at MIT or have been spurred by people working or affiliated with MIT. So these include, for example, one of the first superconducting qubit. He already mentioned some of the first NMR-based qubit, but also very fundamental, important research in quantum phenomena, such as Bose-Einstein condensate or superfluidity. And if you want almost all the algorithms which are nowadays used to show a quantum advantage with respect to classical computer have indeed been developed by MIT researchers. You already mentioned sensing, and if you want, the LIGO gravitational wave observatory is the first real-world implementation of a quantum effect to give a quantum advantage in sensing, being able to detect many more black holes than the original run where the first gravitational wave has been detected. And also, we are looking at things at the nanoscale through quantum sensor, developing nanoscale sensor based on single spin. Last but not least, if you talk to any student doing quantum information, they will tell you that the textbook that they're using is the one shown here, quantum computation and quantum information, that was developed by Ike Chuang from here at MIT. So we really have been instrumental in funding and advancing this field. And of course, we are not stopping there. We are continuing to increase the complexity of the system, like a real scale quantum network between MIT and the MIT Lincoln Lab, much bigger quantum circuit, both based on superconducting qubit or on atoms, or trapped ions, and then the development of new platform for qubits from molecular qubits, and also quantum simulator based on bilayer graphene. So we are really pushing the frontier of this field, and all of this research and education happens all across MIT. This is really a very big effort for MIT. There are almost 100 PIs who are working or are connected to quantum research between campus and Lincoln Lab. And we have footprint in all the schools and in many of the department and laboratory that make MIT. We also have a quite large constellation of different centers. So this research at the moment is a bit sort of diffuse with many different directions. And so recently what we have been trying to push for is to have something which is a more organized center, which will bring together all the people working on quantum in order to really take advantage of the opportunities which are both out there, and also multiply our effort that we can make and our impact that we can make in the field by fostering collaboration, by fostering new programs in which we take the quantum tool that we are developing, and also we work together with people who might use them in bioimaging, in high physics energy, many different applications. So we want really to integrate all these efforts. So what we are launching now is this center that we call Quantum at MIT, as the hub for all of MIT quantum research, but also education and outreach. And we are really integrating both fundamental research and also engineering and applications. So what we want to do is really to foster the exploration and application of quantum systems. In the best tradition of MIT, we are really going from fundamental discovery to impactful technology. So we are bringing forward both of these aspects. And this, we think that this cohesive center will indeed accelerate how we can make an impact using the quantum innovation that we develop at MIT to affect many important world challenges in science and society. So what more precisely are we thinking of doing? Well, we are as I said, we want to foster research and collaboration around 3 different areas, plus, of course, pushing for a more cohesive educational program. So we start from more fundamental research. So if you want, this is really what the people who have worked in quantum for many years are still going to develop, if you want, is quantum for quantum. So we want to improve our knowledge of fundamental quantum theory in order to advance, indeed, the quantum devices that we are developing. Then we also want to connect between, if you want, the innovators in quantum and the potential users of quantum tools across campus and of course also outside campus, in order to enable a new application in science and engineering. And this might still be at the level of things that can only be done in a lab for research purposes, but it already shows the impact of quantum technology. And then, of course, we want to deploy all our tools also in the larger society, and so really foster entrepreneurial spirit of MIT in the quantum area. All of this is going to be, of course, implemented by improving our education and training of our students and of the larger public, by integrating the current, if you want, all the courses that we have in quantum, which are already a very rich resource, but we want to integrate them better in order to build a curriculum, in order to give certificates to students that really make them more attractive to, if you wanted, the quantum industry, which is really blossoming right now. So all of this is what we want to do under the umbrella of Quantum at MIT. And I want to justify a little bit why we are really sort of enthusiastic about this initiative by sort of motivating why quantum is important with two examples. So the first example is going to be on quantum sensing, and the second example instead on quantum computation. So as Peter has mentioned, quantum sensing is something which is happening really already right now. And the idea is to leverage quantum mechanics in order to have sensors which are more accurate than otherwise possible. I already mentioned, for example, the detection of gravitational waves, but also they can enable new regimes of measurement which are not possible by classical sensors. For example, sensing things at the nanoscale, at the same scale where the qubit sensor live, this billionth of a meters. So why is quantum sensing even a good idea, if you want? So we already discussed that quantum systems are notoriously fragile. So we said, Peter mentioned that they can be in two states at the same time, like a cat which can be awake or asleep at the same time, the famous Schrödinger cat. But of course, we typically do not observe such a Schrödinger cat because it is very, very sensitive to any external perturbation. Any molecule of air, any photon which is scattering the cat will just perturb it, which means that it's very difficult to develop a quantum computer, but at the same time, this makes them, this system, great sensor. They will sense really any minuscule perturbation. Of course, we want to keep a little bit the quantum character of our sensor, so it's always a compromise between allowing with extreme sensitivity and still keeping them in a superposition. But you can really find a quantum advantage if you achieve that. So similar to quantum computer, where you can have an exponential improvement with the size of the computation, also for sensor, for classical sensor, you have the signal-to-noise ratio just scale with the square root of the number of sensors that you have or the number of repetition that you do. And instead for quantum sensor, that scaling is proportional to the number of sensors, the number of repetition. So you really have this difference in scaling, which fundamentally make your sensor better. As I say, there are also some practical advantages, such as a nanoscale. And indeed, this is exemplified by what is my favorite quantum sensor, which is a nitrogen vacancy center in diamond. So this is a color center, so a defect in diamond, which can be optically excited. So we typically, what we do is, as in this image, we shine some green light on our little diamond, which is here at the center. Hopefully you can see the bright spot. And the defect itself re-emits light in a different wavelength, in the red wavelength. So I can put on goggles on top of my camera. And now what I see is really the fluorescence which is emitted, the light which is emitted by the defects inside the diamond. So this would make the diamond the color pink. And indeed, it's been sort of studied back in the days in order to make a gemstone prettier, because they would become pink. And it was very valuable type of defect center. But we can use it indeed for quantum purposes. Indeed, this is not only optically active, but it's also an electronic spin. And spin are a little bit like some dipolar magnets. So you can think of them as just the needle of a compass. When you have a magnetic field, the needle of the compass will align with the magnetic field. And similarly, our spin will align up or down with the magnetic field. And the amount of light which is emitted where they're aligned in one direction or the other one changes. And so we can detect the state of the spin by how many photons are emitted. And by knowing what is the state of the spin, in turn, we can know how strong the magnetic field is. So we can use this to have a very, very precise magnetic field sensors, both at the macroscopic scale, but also at the nanoscale. And this has already indeed enabled quite a few applications which are already deployed in the field, and some which are instead still in the lab. So from, for example, doing a navigation based on detecting the magnetic anomalies in the Earth, to detecting individual protein structure by using a single spin sensor to detect the position of all the other proton spins, which are the same that you measure, for example, in doing MRI, in a single molecule, without the need to have large samples and with the ability to really look at the molecules while they're doing their things and finding some small spots for drug development or to understand better the composition. Also, typically you do MRI of a full brain, but here people were able to detect the signal from a single neuron. And again, by looking at things at the nanoscale, we are able to measure, for example, magnetic materials and their properties. So quantum sensing is really a very exciting opportunity for quantum research because it's already delivering some tools and some devices which can help real application right now. The other big hope, of course, for quantum science and engineering is quantum computation. And here I have a few slides, which I borrow from my colleague Vladan Vuletic, also in the physics department. And I wanted to show this because in some sense, what I will show you is the jump from hope to the glory, hopefully avoiding the hype. So I'll read this quote from Richard Feynman, who is considered one of the fathers of quantum science and engineering. He said back in 1983 that in principle, we can make a computing device in which the numbers, so with 0 and 1, are represented by a row of atoms, with each atom in either of the two states. That's our input. Then the Hamiltonian started evolving the wave function. The ones move around, the 0 moves around. Finally, a particular bunch of atoms represented the answer. And he went on to say, nothing could be made smaller, nothing could be more elegant. But Feynman was still wondering, can we do it? And indeed, this question is sort of hovering over the field for quite a long time. And actually, the answer is actually that we can implement exactly what he was saying in the experiments today. So what you're seeing now, these bright dots, are individual atoms, Rydberg atoms, which are moved around by using optical tweezer. And again, every time that the two atoms come together, we have, as Feynman was saying, the Hamiltonian making a small computation between the two atoms. And finally, these atoms on top here, they will encode the final answer what you want to read. So my colleagues have indeed used this to already implement a particular quantum algorithm, which was an optimization problem, in a way which is a sort of combining both classical machine learning with a quantum computer, because we don't have the full power of quantum error correction that Peter mentioned yet, but it's coming along. So we are really moving forward and already having a large number of qubits, large devices, which are really progressing very, very fast. So I think that we are already sort of late in time. So I will just leave for 1 second this slide here, as hopefully is a seed for some discussion among all of these. And then I will just end up my slide share, and hopefully Peter and I can indeed answer some of your questions.
Okay, thank you. Thank you, Paula. I think we have time for some questions. Paula, you can see the chat.
Yes, I'm slowly reading through.
There's a question. I'll ask you a question, and then you can ask me a question. Okay, how is the uncertainty principle consistent with quantitative computing?
Oh, yes, that's a very nice question. Yeah, so what we are doing is to measure at the end of the computation the answer of the computation. So, of course, one wants to have a definitive answer in the end. A lot of the algorithms which have been developed deal with the fact that the quantum measurement will give out a random result. But of course, the probability with which the results come out are very well determined by the problem at hand and the algorithm. So the algorithm themselves need to be built in order to take into account that the measurement will have a sort of a probabilistic result. And if you want to increase the probability that you get the correct answer. In some sense, this is why, if you want, not all algorithms are more efficient on a quantum computer. Only some special algorithm can sort of exploit both the superposition principle that Peter explained, entanglement, and in the end, get the correct answer in an efficient way. So indeed, if you want, the uncertainty in principle in the sense of not being able to measure two different observables at the same time is not like a challenge, but the randomness of the measurement outcome does indeed need to be taken into account. And that's what the powerful quantum algorithms do, and the one which do not work, they're not as good.
So just before the next question, I just want to say, we went through a lot, and we're a little bit pressed for time, but we're going to stay on a little bit later because the questions are usually the best part. And so if you have to go, hop off. But if you want to pick up on the questions, they'll be on the recording that you can look at sometime next week.
Okay, so I will go, I guess, to the next question.
Sure.
Is quantum tunneling considered a statistical phenomenon? For example, when a particle escapes a nucleus in radioactive decay, like alpha decay, the geometrical fluctuating nucleus over time eventually expels the particle?
Yeah, I mean, so tunneling is a statistical process. When you So quantum mechanical tunneling is, if you go back to the 2L potential, it is actually possible for a particle to go through from one side to the other by actually going through a region that classically it wouldn't be allowed to go through. And that is a statistical process in that on average, you can tell how long it will take. But for an individual particle, it might take a very long time. Let me see a question for Paula. Okay, what will quantum computing do to the energy per calculation? So we think of storage and computation as costless, but blockchain, crypto, and LLMs and AI are increasingly expensive energetically. So, Paula, why don't you give your take on that, and then I have an interesting thing to say.
Yeah, sounds good. So there are, like as we said, there is an intrinsic quantum advantage for some algorithm, as we say, not all possible algorithm. So in some sense, if it takes you an exponential smaller number of quantum bits with respect to bits, or an exponentially smaller time to do a calculation, immediately you will have an energy saving, which is linked to that. Now, of course, this is as long as doing a single quantum gate does not take an exponentially larger amount of energy, which will counteract. But currently, there is no physical reason why that should be. Actually, the computation should be not expending any energy if it were perfect, because the evolution in quantum mechanics conserves energy. But okay, we deal with real systems where indeed you have an energy cost. But there is no reason why you should have an exponential increase. There is right now, there is, if you want, a new way of approaching the quantum advantage, which is also indeed to consider whether you can have a quantum energy advantage even if you don't have a computational one. So as I mentioned, if you have a computational advantage, unless your system is crazily heavy, which it should violate some physical law, you should have at some point an energy advantage. But maybe you can have an energy advantage even before you have a quantum computational advantage. And that's, if you want, an area of research where we don't have an answer yet, but it's very interesting, especially because indeed the energy consumption for calculations is increasing astronomically.
Yeah, so my day job is actually, I run a data center for MIT in Holyoke, and there's I mentioned Moore's law. There's also Dennard's law, which says the power per computation decreases by a factor of 2 every 2 years. That stopped happening about 2006, and now the power per calculation gets better every 4 years. And this really means something, because the electricity bill for our data center at Holyoke is about $1 million a year.
Hey, I can ask you another question. So Professor Shore predicted authentication difficulties with the arrival of quantum computing. So this is the Q day, if you want. How close do you think post-quantum cryptography is to overcoming this predicted hurdle?
That's a really interesting question. The National Institutes of Science and Technology, which one of the big things they worry about is encryption, actually had a competition for post-quantum or quantum safe classical encryption algorithms that concluded about a year and a half ago. And so these are algorithms that are provably safe against a quantum computer, even though one doesn't exist. They identified 4 algorithms, and they have funny names like Bike and Psych, and I don't remember the others. They identified 4 algorithms. There were papers that showed they were quantum safe. Within a week, someone broke one of them using a classical computer. The other 3 are good so far, but this is really a new and complex field, and I wouldn't say we're out of the woods yet. Okay, here's a good one for you, Paula. A lot of the qubits seem to depend on electrons. They are fermions, which can't be in the same state. That seems to limit the number of available states a set of qubits can be in. How does that affect things?
Yeah, so this should not be a problem. Typically you want, in any case, your qubit to be distinguishable. So like the problem of fermions not being able to occupy the same state arises when fermions are indistinguishable. So 2 neutronic spins, for example, that you cannot really distinguish, or 2 electrons that you cannot distinguish. But for a quantum computer, you do want to know where you're storing your 1 and 0, which correspond to a given number, to a given answer. So typically your qubits will indeed, even fermionic, be distinguishable, so they can occupy the same state. It's not a problem. There is like they can be distinguishable because they're in different locations, for example, of your computer. Typically that will be a way so that you're also able to sort of detect it separately. So you have additional degrees of freedom that you're using to sort of like overcome this problem, if you want, this Pauli exclusion principle. Oh, okay, Peter, I like this for you. You haven't really talked about the hype. Can you say more about that?
Oh, okay. Yeah. One doesn't like to dwell on the hype because it's embarrassing, but it's also kind of enchanting. So the hype really is that there are a lot of folks with money who say, let's go ahead and start building large-scale quantum computers with the prediction that quantum error correction will get solved in a year or 2. And I was earlier this year, about a month ago, here in Washington, D.C., at the World Quantum Congress, which was a trade show for quantum technologies. And, there were there were people who, if you had a few $1 million, would sell you a quantum computer that has 60 qubits in it. They're not error corrected, and you can do some things if you don't have quantum error corrections. You're just not going to beat anyone. You're not going to beat a classical computer. And it was hard for me to tell whether these people actually knew this or not. And so that's one element of hype. As Paula has mentioned a number of times, that there is not clarity right now on what kinds of problems quantum computing will do much better than classical computing on. And this is called quantum advantage. And there are a lot of people who are selling quantum gear who are just ignoring this, and you know, they'll sell you a quantum computer, and it will tell you that well, we heard one report about a company that's selling things to airlines to more efficiently pack their cargo containers. It's an air logistics company, and you know, this is a problem that was solved a long time ago by people like Yossi Safi and Cynthia Barnard. You know, people have been optimizing things for a long time, and they're pretty good at it. So, you know, I don't think the hype is terrible as long as there's kind of a core group of people who are ignoring it and just working ahead. Okay, here's so we'll make this the last question. So for you, Paula, it was mentioned that quantum at MIT will involve every school at MIT, including Sloan. Is there a good non-physics or even non-scientist or non-engineer book on understanding of quantum?
Ooh, I hate this type of question because I'm always like, I'm so biased because I know this stuff. So it's really tough for me to judge what is good for people who don't have a background. I think that there are like a lot of resources. So one thing that you might find useful on MIT X Professional, and maybe somebody can correct me exactly what this is, but I'm sure that we can share the links. A few faculty at MIT have put together a course for professionals. So indeed, that's exactly what you're asking for. And this is done through videos, through some follow-up problems, etc. So it's really a good way of learning things a bit more in depth. So I think that these are, I would say, trusted people because they're MIT professors. And they did like a tremendous job in presenting the fundamentals from both like if you wanted the theoretical part, but also the hardware part. So I think that's a great resource. And that's also something that we want to do with Quantum at MIT to enhance even more the offering that we have for alumni, for the broader community that might become interested in quantum, because indeed it's a technology which is exploding, and we see an increase in curiosity and interest from all parts of the world.
Thank you. I'll add. We have Paula and I have a colleague, David Kaiser, who is actually quite remarkable. He has 2 PhDs, one in the history of science and the other in he studied cosmology with Alan Guth, and he has a book called Quantum Legacies, which are stories of quantum mechanics. There's some quantum computing there, but it is just a lovely book. And David is a terrific writer. And the other place is where you can kind of follow stuff is Quanta Magazine, and that's quantamagazine.org, Quanta magazine.org. This is a publication by the Simons Foundation. The quality of writing is very high. And they have a few stories each week on mathematics, physics, quantum things, and brain and cognitive science. So it's kind of an interesting place. I think that's all we have time for today. I want to thank Paula. It's always fun doing things with you, Paula. We're going to do more things.
Yeah, likewise.
And I also want to thank the MIT Alumni Association for bringing us together around fascinating and significant topics. And it's just a great thing for us to connect with all of you, our alumni and our students who are out there. And of course, we all want to thank you for your tremendous support of MIT. I was a department head for a long time, and I really appreciated the help I got from our friends and patrons. So thank you very much. And please keep coming back, and please keep supporting us. And so with that, I'll conclude and say goodbye. Thank you very much.